All right, welcome to Organic Chemistry. We're going to continue our discussion of cyclically conjugated systems, that is aromatic or anti-aromatic, or, well, non-aromatic ones are not cyclically conjugated systems. And specifically here, we're going to start looking at the reactions of aromatic rings. Now, in our previous discussion, we talked about what is an aromatic system, and we noticed that some of the properties of aromatic systems is that they did not behave like alkenes. In particular, we said that they don't behave they don't have reactions like the reactions of alkenes. For one, they are less reactive than alkenes. And for two, they don't do addition reactions like alkenes do. So this is a slide that I showed previously in the last presentation. And we see that alkenes undergo characteristic electrophilic additions, where first an electrophile and then a nucleophile add across the double bond, as shown in the two examples on the left. But those same reactions don't happen with aromatic rings like benzene. Instead, a different reaction happens. And I mentioned at that time that this is, well, it's obviously a substitution because there's a hydrogen that starts at this position that's being replaced by a bromine. So we're substituting one atom for another, but this is not an SN1 or SN2, nor is it a radical halogenation, but this is some other mechanism. And that's what we're going to look at in this presentation, is this reaction in particular and reactions like it. And we're going to discuss these and refer to them as electrophilic aromatic substitution reactions. That's the characteristic reaction of aromatic rings. So, what is electrophilic aromatic substitution? To start with, let's just reconsider alkene chemistry. If I have an alkene, the alkene pi bond can reach out to some electrophile to form a carbocation intermediate. And then if a nucleophile comes along, we get the addition product, right? So that's, every alkene reaction, well, not every alkene reaction, but so many of the alkene reactions followed essentially this pattern or some slight variation on this pattern. Let's take an aromatic ring and let's imagine that if one of these pi bonds reaches out to an electrophile, we would get a carbocation, just like with the alkene chemistry. And you could imagine a nucleophile coming a point and leading to an addition product. But what if instead we lost a hydrogen from the next position over to form a double bond? Remember when we first learned about SN1 and E1 reactions, we saw carbocation intermediates, and we said from that point one of two things could happen. A nucleophile could come along, or you could lose a proton to form a pi bond. That's the difference between SN1 and E1. These two competing products are like the second half of SN1 versus the second half of E1. But I just told you that addition reactions don't happen. So we don't get this top type of product. Instead, we get the bottom type. Now, why would that be? Well, let's go back to what we learned last time about aromatic systems and Huckel's rule. Huckel would define this species as an aromatic ring. Going from here to here, we would say that this is non-aromatic. Remember, something that is aromatic is much more stable than something that is non-aromatic. And so while we can do this, this is going uphill, and that's why aromatic rings are relatively unreactive. That is, they don't react as readily as alkenes. They're particularly stable. But what about going from here to here or here? If I go to here, I'm going to another non-aromatic species because I don't have cyclic conjugation. But if I go here, I'm going back down to aromatic. So energetically, it's like going from low to middlingly high and staying at middlingly high. Or going from low to middlingly high, and then back down to low, back down to something much more stable. And so it turns out that is what is observed, the electrophilic aromatic substitution product. Now notice this is nothing new in terms of the arrow pushing, Pi bond reaching out to electrophile. We've seen that again and again with the electrophilic addition reactions. And loss of a proton from the position adjacent to a carbocation to form a pi bond. Well, that's the second half of an SN1. I also want to point out that that central intermediate is stabilized by resonance, even though it is non-aromatic, and therefore it is certainly much less stable than an aromatic system. It is a resonance-stabilized carbocation. And little piece of chemistry trivia, that's called the Wayland intermediate, and I'm sure Wayland's grandkids are happy that I mentioned him. All right, let's look at some specifics, and let's start with bromination. If I treat a benzene ring with Br2 and iron tribromide, I will form bromobenzene. Okay, what's going on? To do that, we first have to start out by figuring out what is this iron tribromide thing. It's a Lewis acid. It's an iron with 3 bromines, and it's going to act as an electron acceptor because it's got an empty valency, basically empty orbital that can accept 2 electrons. So let's imagine reacting with Br2 where bromine reaches out with a pair of electrons to form a bond to iron. If we do that, we're going to get a formal charge of +1 on our bromine. And that's going to make this pretty unhappy. In fact, if I've got a formal charge of +1 on a bromine, well, we've seen examples before with oxygen where we made an extra bond to oxygen and we had a formal charge of +1. And since oxygen is relatively, well, it's the second most electronegative element, it would rather have electrons to itself. We relatively easily break a bond. In this case, this is going to make it very easy to break one of these 2 bonds. If I were to break the bromine-iron bond, well, I'd be going back to here, so I probably should have drawn this as a reversible arrow. But I can also break this bond. If anything, even a very weak Lewis base electron pair donor comes along and reaches out to this bromine, that's going to make it very easy to break this bond. And that's indeed what happens. Remember the reaction of just an alkene with Br2. We thought of the Br2 as a combination of quote-unquote Br plus and Br minus. In this case, this is an even more souped-up version of Br plus, because by coordinating to iron, that's made it that much more easy to break this bromine-bromine bond. So pi bond reaches out to Br2. Iron tetrabromide is a byproduct here to form the resonance-stabilized Wayland intermediate, and then loss of a proton leads to our product. Now, this theme we are going to see again and again. Pi bond reaches out to some electrophilic species. We form a intermediate, and then loss of a proton leads to the substituted product. And it turns out all electrophilic aromatic substitutions are going to follow the exact same pattern. They're just going to differ in terms of what is the electrophile. And we can do other reactions as well. Let's just take a real small baby step from the previous example. In the previous example, we took an aromatic ring, bromine and iron tribromide. If we took chlorine and iron trichloride, you're probably not surprised to see that the exact same thing happens. And it happens in exactly the same way. Cl2 coordinates iron trichloride to make a souped-up version of quote-unquote Cl+. It's still not free Cl+ floating around, but this is going to be a very strongly electrophilic version of a chlorine, a source of a chlorine plus. If the pi bond reaches out to the chlorine to make an intermediate, loss of a proton leads to the chlorobenzene product. Okay, let's do a little bit tougher. If I take benzene and I react with fuming sulfuric acid, that's a combination of SO3 and H2SO4. Well, SO3, here's a Lewis structure for SO3. Notice we have d orbitals with sulfur. So yes, there's more than 8 electrons around there, but that's okay because we're below the second row of the periodic table. You've seen, for instance, H2SO4 having a Lewis structure that seems to violate what you know about bonding as far as the octet rule as well. But if SO3 protonated That is, a pi bond from the sulfur-oxygen pi bond reaches out to the acid. Now notice we've seen lots of examples of reactions where a pi bond reaches out to H+. It's just here it's an SO pi bond, as opposed to most of the previous examples we've seen that involved carbon. But this SO3+, well, that's our ultimate electrophile. If our aromatic ring pi bond reaches out to the electrophile, the sulfur, to form an intermediate, loss of a proton leads to benzene sulfonic acid. Okay, again, same mechanism, just a different electrophile. So these conditions of SO3 and H2SO4 are really just a source of our electrophile. And once we've got an electrophile, the benzene ring is going to react with it in exactly the same way. Nitration. If I take nitric acid and sulfuric acid and benzene, I'll make nitrobenzene. Now, here's the Lewis structure of nitric acid. And of course, it's right there in the name. It's an acid, right? Nitric acid is a strong acid. And so we usually think of it donating a proton to somebody else. But if there's a stronger acid around, well, it can actually act, in this case, as a Bronsted-Lowry base. Because remember, acid strength, it's not a black-white thing where some things are strong and some things are weak. It's really a ranking of stronger to weaker. And sulfuric acid is even stronger than nitric acid. And so it can protonate nitric acid. And if the oxygen on the left gets protonated as shown here, we see something that should look familiar to us. An oxygen with 3 bonds, formal charge of +1. Let's break a bond. If I were to break one of these bonds, I'd be back over here. But if I was to break this bond, and that's going to be pretty easy to do, because notice we've got 2 positively charged centers right next to each other. And that's going to be, like charges repel, so it's going to be really easy to break this bond. And if we did so, we'd make our ultimate electrophile. So this is the electrophile. So this set of conditions is really just a way of making our electrophile, which acts with benzene ring in the exact same way that our previous electrophiles reacted with benzene ring. That is, pi bond reaches out to the NO2+, intermediate, loss of a proton, regenerating that pi system to get an aromatic ring back, nitrobenzene in this case. 2 more. Friedel-Crafts alkylation starts with some alkyl chloride and aluminum trichloride, some, I should say, really secondary or tertiary alkyl chloride and aluminum trichloride. I'll talk about primaries in a little bit. But if I was to take this, well, aluminum trichloride, aluminum is right below boron on the periodic table. It doesn't have a full octet, and so it's going to act as Lewis acid. And so if chlorine reaches out to aluminum, we're going to put a plus charge on chlorine. And you're probably not going to be surprised that if I've got a plus charge on that chlorine, the next thing I'm going to want to do is break one of the 2 bonds to that chlorine. I could break the aluminum-chlorine bond, which would bring me back where I started. But if, on the other hand, I broke the carbon-chlorine bond, I get a carbocation intermediate. That carbocation is an electrophile. It's a pretty strong electrophile, right? It wants to grab electrons from somebody, and if it does so, from a benzene ring will lead to an intermediate. Loss of a proton leads to a substituted product. Notice this doesn't have to be 2-chloropropane. This could really be any secondary or tertiary alkyl halide. Doesn't have to even be chlorine. Could be bromine or iodine or as well. And the last of our electrophilic reactions is similar. It's a Friedel-Crafts acylation. So instead of adding an alkyl, that's just a hydrocarbon, just a carbon-carbon-carbon single bond piece, if we add a thing with a carbonyl group on it. So this is an acid chloride. It's derived from acetic acid. We'll learn about acid chlorides later on when we talk about the different derivatives of carboxylic acids. But this does the same, in really the same way. Aluminum trichloride, Lewis acid. It can coordinate to the chlorine. And if we've got 2 bonds to chlorine and 2 lone pairs, we have a formal charge of +1. That chlorine is more stable when it's neutral. So if a bond is broken, that will lead, in this case, to our ultimate electrophile. It's an acylium ion. If a pi bond is out to that acylium ion, we get our intermediate. Loss of a proton leads to product. Again, notice that we're following the exact same process. In terms of the benzene ring, we're following the exact same process every time. Pi bond reaching out to electrophile, loss of a proton leading to the substituted product. This set of conditions, a Lewis acid, such as aluminum trichloride, and an acid chloride, just leads to the carbocation, where the cation where I've got this piece, I've gotten rid of the chlorine, I've got a plus right here. So this piece here. So of course it doesn't have to be acetyl chloride, there could be other carbons out here, and that would of course lead to other carbons out here in the product. So just to sum up here, we've seen 6 reactions that from the standpoint of the benzene ring were all the exact same thing. Just these different sets of conditions were all sources of different E+, different electrophiles. Bromine and iron tribromide was a source of, in quotes, because these aren't really floating around free, positively charged bromine. And chlorine, really the same thing, just chlorine. Fuming sulfuric acid is a source of SO3+, and so if I react a benzene with that, I will end up, so I should have stated up above, so I end up with whatever I've got here at this position. So I get a bromine here, or a chlorine here, or an sulfur with 2 double bond oxygens and an OH here. Or if I have nitric acid and sulfuric acid, I end up with an NO2 group over here, a nitro group. Or I end up with an alkyl group attached here, or a CO double bond and then some carbon chain here. So in this case, an acetyl from this particular example. But all of these reactions are really the same thing, and that's what I want to emphasize again and again. But now we've got a bit of a problem. If I had taken benzene, like in the cases I took before, and reacted it with some electrophile, okay, it doesn't matter where I put that bromine, because benzene is completely symmetric, right? If I put the bromine here, or here, or here, or here, or here, or here, those all give me the exact same product, because benzene is completely symmetric. But what if instead I already have one substituent on benzene, and now I treat this with Br2 and iron tribromide? Where does the bromine go at this point? Now here the bromine is our second substituent. It could go adjacent to the first substituent, so that's called ortho. It could go 2 carbons over, that's called meta, or it could go para. But if you go to the lab and try this out, you find out that you get a mixture of ortho and para, and you do not observe any meta. Okay, so let's say you go and you take acetophenone and you decide to treat it under the same conditions. And you say, well, you know, I got these very possible products, but with methoxybenzene, by the way, it's also known as anisole, I got ortho and para, so maybe you might expect to see that. But in this case, you only see the meta. What's going on here? Is this something to do with Br2 and iron tribromide? Let's try a series of other reactions. Let's take anisole, that is methoxybenzene, and treat it with nitration, or Friedel-Crafts alkylation. And then let's take acetophenone and treat it under nitration conditions, or Friedel-Crafts alkylation conditions. And we see the same patterns that we saw with the first example. So, and I didn't put these up, but it'd be the exact same patterns would be observed if our electrophile was our electrophile source with chlorine and iron trichloride, fuming sulfuric acid to put on an SO3, or an acetyl chloride and aluminum trichloride in a Friedel-Crafts acylation. We would get, with methoxybenzene, we would get ortho and para products in some mixture, and in acetophenone we get only meta. So notice that the electrophile isn't affecting this at all. The difference is all about this methoxy versus this carbonyl group. Let's see if we can understand why having a methoxy on a ring would lead to a mixture of ortho and para products, and then we'll go further to see why having a ketone adjacent to my benzene ring would lead to meta products. But let's start with the methoxybenzene. Let's just imagine methoxybenzene reacting with some generic electrophile, because the previous slide showed us that it really doesn't matter which electrophile we're using. It could be any of those, or there's other electrophiles out there that work in electrophilic aromatic substitution. We just showed those 6. But let's imagine our electrophile could react at the ortho, meta, or para position to give us a carbocation intermediate. And what we're going to do is we're going to consider each of these and decide which is best. Okay, so in each case, I can draw resonance forms, right? Because I've got this plus charge in my intermediate, and I've got pi bonds, and I can draw a series of resonance forms where pi bond moves here, putting a plus here, pi bond moves there, putting a plus there. And we do that here and here. That's true of each of these. We're going to get some resonance forms. But I left some gaps here for a reason. Let's specifically take a look at this resonance form of our resonance stabilized intermediate. Here I've got a plus charge, and right next door I've got lone pairs on oxygen. And one of those lone pairs can reach out to be shared with that plus charge. Shifting here to be shared there, to further delocalize our positive charge, not just across 3 carbons in the ring, here, 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 but also onto the oxygen. In the bottom case, we see something similar. I've got these 3 resonance forms that have the positive charge delocalized within the ring, but at this resonance form, notice I've got a lone pair adjacent to the positive charge, and that lone pair can reach over and help share that charge, help stabilize that charge. And so, again, we get an extra resonance form due to that lone pair on oxygen. Now let's come back and look at the meta. Notice none of these 3 structures, this one, or this one, puts the plus charge right next to the oxygen with the lone pair. So we cannot get, in this case, the meta case, we cannot get that additional stabilizing resonance form. So the top one and the bottom one have more resonance, that is, they stabilize the positive charge more by spreading it across additional atoms, and therefore energetically those are more stable intermediates relative to the meta intermediate, and therefore those are the ones that are observed. The meta one is not observed. So if I take methoxybenzene and I treat it with any electrophile, I am going to end up getting a mixture of products, some of which put the electrophile ortho to the methoxy group, and some of which put them para. Alright, let's go look at the carbonyl species, acetophenone is the name of it, and let's do the exact same consideration. I can have electrophile react either ortho, meta, or para to the initial substituent, the carbonyl, and I'm going to get a series of resonance stabilized carbocations. That is where I can delocalize the positive charge through this ring, around this ring, based on various resonance. This goes there, positive here, this goes there, positive there. And notice I can do the same here. But I'm going to highlight these 2 resonance forms for a reason. This resonance form puts a plus charge adjacent to a carbonyl. And the one thing we know about a CO double bond, if we don't know anything else, is that it's got a partially positive center. So this resonance form puts a positive charge directly adjacent to a partially positive center. We see the same thing down here with the para. notice we do not see the same thing with the meta. But that's going to be unfavorable, because putting a plus next to a partial plus, Coulomb's law says putting opposite charges close to each other is good. Putting like charges close to each other is energetically bad, because like charges repel. Since resonance means a weighted, a resonance stabilized thing is really an average of the various important resonance forms that go into it, it's weighted towards the more important resonance forms. And the two that I've highlighted in red turn out to be insignificant contributors to the overall structure. And therefore, let's just not count them at all. And therefore, the top and the bottom case only have two resonance forms helping stabilize that positive charge. But the middle case, the meta case, has more, has three. And therefore, that is the observed one, because it goes through the more stable intermediate. So the methoxy is called an ortho-para director because it has lone pairs that can interact with the ring. And whenever I put an electrophile either at the ortho as shown or para position, one of the resonance forms puts a positive charge right next to that oxygen with the lone pairs. You know, there's lots of things that have lone pairs. Doesn't have to be a methoxy, could be other oxygen-containing groups, could be a nitrogen, could be a sulfur, halogens, other elements as well. Even an alkyl group is a slight electron pair donor. Any electron donating group will help stabilize a positive charge, and therefore all of these groups are ortho-para directors. That is, if I started with any one of these and I treated them with electrophilic aromatic substitution conditions, the electrophile would either go ortho or para, or ortho or para, or ortho or para, or ortho or para. On the other hand, a ketone was a meta-director. And it's a meta-director due to the badness of the resonance form shown. That is, resonance forms that put a plus charge directly next to that carbonyl. That happens when my electrophile comes in either ortho or para. And so therefore a ketone turns out to be a meta-director, because that turns out to be better energetically. Well, really, anything that puts either a partially positive charge or a fully positive charge adjacent to the ring has the same effect. So any CO double bond containing functional group, a ketone, an aldehyde, a carboxylic acid, or an ester as shown here, or other polarized pi bonds like an SO pi bond or a CN triple bond, those are also meta-directors. Or the nitrobenzene and the ammonium, the tetrasubstituted nitrogen species, put a full plus charge adjacent to the benzene ring. All of these things are meta-directors. And so if I was to bring in any electrophile with these guys, it would go here, or 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 here, respectively. Now let's just throw a little bit of a monkey wrench in the works, just to make things a little more exciting. Ortho-para groups and ortho-para directing groups and meta-directing groups have an additional effect. Aside from setting, helping determine which isomer of product is formed, they also will either, respectively, make the aromatic rings more reactive or less reactive. Ortho-para groups are generally activating groups. So for our comparison, let's take this molecule, which is called biphenyl. If I treated it with Br2 and iron tribromide, notice either one of these aromatic rings, it's a symmetrical thing. I could put my bromine on, this has two aromatic rings, so my bromine could either go over here or over here. Respectively, it wouldn't really matter. But now, let's take methoxy. This is biphenyl, by the way. This two benzene rings attached by a bond is biphenyl. Let's take methoxy biphenyl. if I treat this with Br2 and iron tribromide, a methoxy group, remember, has lone pairs that donate to the ring. And that means that this ring has a little bit of extra electron density relative to this ring. Which ring do you think would be more likely to react with a positively charged species? Yeah, it's the one that's got extra electron density. And so what we say is that the methoxy has activated this ring. It's made it more reactive. And here I can compare it to this ring. This one's more reactive than that one. And so what we see is our bromine reacts on this side because this ring is more reactive. Methoxy is an ortho-para director. Notice the para position is blocked, and so the bromine has to come in ortho in this particular case. On the other hand, meta-directors, remember a nitro group puts a plus charge next to the ring, and that's going to help to really withdraw electron density away from the ring. In our discussion of the Diels-Alder reaction, we talked about electron donating groups versus electron withdrawing groups. And methoxy is an electron donating group, and a nitro is an electron withdrawing group. It's going to suck electron density away from this ring, and therefore this ring will be somewhat electron poor, especially when you compare it to this ring over here. Now which one is more likely to reach out with electrons? This one, the one that hasn't been affected. So this is kind of at its benzene's default, and this one is less reactive than benzene. And so in this case, this one will react. And so we'll get this, and probably also some ortho, just because a phenyl is going to act as an ortho-para director. So I'm going to get product either here or here preferentially. On the whole, things that are ortho-para directors, are electron donating groups, are generally activating. And so those rings that have ortho-para directors tend to be more reactive than benzene, and things that have meta-directors tend to be less reactive than benzene. Except halides are strange. I don't want to spend a lot of time on it, but halides like chlorine or bromine are ortho-para directors, but they're also slightly deactivating. It really comes because of the fact that you've got two effects going on, one involving the pi system and one involving the sigma system. I'm not going to get any further, go any further into it than that. And finally, I just want to note that if you've got a lot of deactivating groups, let's say you've got 1 or 2 or even 3 deactivating groups attached to a benzene, it might not do electrophilic aromatic substitution at all. Or you'd have to, if it does it, it might do it less efficiently, that is more slowly, and you might have to heat things up more to get it to react. So deactivated rings are, well, by definition, less reactive than benzene. The final thing I want to do in this discussion of electrophilic aromatic substitution is note 2 sets of reactions. So these are, well, quote-unquote, multi-step syntheses. If I took benzene and I treated it with chlorine and iron trichloride, and I took the product of that and treated it with nitric acid and sulfuric acid, or let's do another multi-step synthesis, 2-step synthesis, that takes the exact same sets of conditions but reverses the order. So what would happen? If I took benzene and treated it with chlorine and iron trichloride, as we know, we'll make chlorobenzene. But chlorine is an ortho-para director. And so if I nitrate this, I'm going to get a mixture of, here I've shown, the para-nitrochlorobenzene and the ortho-nitrochlorobenzene. I suppose it would be chloronitrobenzene because it's alphabetical. But I'm going to get a mixture of the ortho and para products. Now let's just swap out the order. Let's take benzene and treat it with nitric acid and sulfuric acid, make nitrobenzene. But a nitro group is an ortho-para director. No, it's not. Scratch that. It's a meta-director. Anything that puts a plus charge or a partial plus charge, and this puts a fully positive charge adjacent to the ring, is going to be a meta-director. Scratch what I mistakenly said there. It's a meta-director. And therefore, we're going to get meta-chloronitrobenzene. Notice, same reagents, just a different order in which we added them leads to different overall constitutional isomers, or regioselectivity would be probably the jargony way to say this. In addition to electrophilic aromatic substitution, there are other reactions of aromatic rings as well. I'd like to point out that the position adjacent to the aromatic ring is particularly important. This is called the benzylic position. That is a carbon that's right adjacent to an aromatic ring. And it's important because reactive intermediates, including carbocations and radicals, are particularly stable at this position. Now, this is a primary position, so you might say, well, why is a carbocation okay here? Because this carbocation is adjacent to a bunch of pi bonds, so I can draw a bunch of resonance forms. And so reactions that involve a positive charge or a radical at this position occur readily. For instance, in the top case, benzyl chloride, if you heat it up with water, you'll make benzyl alcohol. This is an SN1 reaction. Chloride ion goes away to leave a positive charge at this position. But that's reasonable in this case because it's a benzylic, it's radical stabilized carbocation. And then water comes along after loss of a proton. You get your product. This is just a straight SN1 reaction. Or here's an addition reaction where I've got an alkene. After I protonate, I end up with a carbocation at the benzylic position, and then chloride adds. Here's, to give an example case, ethylbenzene, when I treat it with Br2 and light, remember this is a free radical halogenation, and it goes via a radical intermediate, which happens selectively at this position. There are various reactions that take advantage of the benzylic position. The important one is the Clemmensen reduction. Clemmensen reduction is a reduction of a ketone to an alkane with zinc mercury amalgam, HCl, and water. In the process, I'm not going to go through the mechanism. It involves electron transfers and protonation, loss of water, so ultimately the oxygen gets protonated after various electrons. The oxygen gets protonated, the carbon gets protonated, and we end up with water and an alkane. Now, why is this useful? One is, let's imagine I wanted to do a Friedel-Crafts alkylation to make one phenyl propane. So I say, well, I'm going to take one chloropropane, an aluminum trichloride, make a carbocation, and it's going to react electrophilic aromatic substitution to make this. Right? It doesn't work. Instead, you get 2-phenylpropane. Why? Well, what's the mechanism of Friedel-Crafts alkylation? Chloride leaves to make a carbocation. And in this case, if the chloride left here to make a carbocation, it would be a primary carbocation, which even if you could form it, an aluminum trichloride, that's a strong Lewis acid, it might rip this off. Probably almost simultaneously, this thing would rearrange to the more stable secondary carbocation, which then would act as the electrophile. So we can't do a Friedel-Crafts alkylation with a primary position, but Friedel-Crafts acylation. Because in this case, after you remove this chlorine, you get a positive charge here. It's not a primary position. It's got this oxygen that helps stabilize it with resonance stabilization. And that'll get this product. Okay, but we wanted this product. Let's say that's the drug that cures all the world's ills. Well, we can take this ketone. We can take this ketone and reduce it using Clemmensen reduction conditions to give us 1-phenylpropane. So notice it behaves as if we had done a Friedel-Crafts alkylation at a primary position. We can't actually do that, but in doing these 2 steps, we've done kind of a workaround to get at our desired product via a Clemmensen reduction. Or, to take another example, let's take benzene and let's treat it with 3 sets of conditions. So there's going to be a 3-step, multi-step synthesis. But let's say we do this in lab, and one student does first the Friedel-Crafts alkylate or acylation, then a bromination, then a Clemmensen reduction. And their lab partner, let's say they didn't read the instructions right and they get mixed up which order they're supposed to do the steps in. Let's see if it makes a difference. If I take benzene and I treat it with acetyl chloride and chloride, this is the Friedel-Crafts acylation. I'll make acetophenone. And if I treat this with bromine and iron tribromide, this is going to put on a bromine, but the carbonyl, the ketone, is it's a meta-director. And so my bromine is going to come in here or here. It's the same thing. I'm going to make the meta-bromoacetophenone. And then when this is treated with zinc-mercury amalgam, we get the meta-bromoethylbenzene. But the lab partner, who didn't read the directions right and did things in the wrong order, okay, they did the Friedel acylation, that's the same. But if they do the Friedel-Crafts acylation on this, ethylbenzene, but an ethyl group is an ortho-para director. So when they treat this with bromine and iron tribromide, they're going to get a mixture of products, some para, as I've shown here, and some ortho. So they'll actually get a mixture of two different products. Notice by changing up the order in which we do these, we've essentially taken the side chain and we've gone back and forth between being either a meta-director. In this case, the side chain is a meta-director, and so the next group comes in meta. Or here, an ortho-para director, so our next group comes in either, well, para as shown, or ortho. In addition to reduction at the side chain, that's the Clemmensen reduction, the side chain can also be oxidized with potassium permanganate. If I take some alkyl benzene and I treat it with basic potassium permanganate, upon neutralization we will get benzoic acid. Now notice, in the process, we broke carbon-carbon bonds. It doesn't matter how long this chain is. In the end, all of these extra carbons are going to get broken off, and we're just going to end up with this carbon oxidized to a carboxylic acid. Again, I'm not going to go through this mechanism. It does involve radicals, electron transfer. It's not worth going through. But this is a good way of making benzoic acids. For instance, if I was to take toluene, that's methylbenzene, and treat it with bromination conditions and oxidation conditions, but if we just changed up the order, let's see what happens. If I brominate, now this isn't bromine and Br2 and light, this is Br2 and iron tribromide, so I'm going to do an electrophilic aromatic substitution. A methyl group is an ortho, so we're going to get a mixture of two different regio isomers, para as shown, and also ortho. And then if this is treated with potassium permanganate, basic potassium permanganate and water, followed by acidification, you would get the para bromobenzoic acid, and also some of the ortho. On the other hand, if we started with toluene and we treat it with potassium permanganate, followed by acidification, get benzoic acid, but benzoic acid puts a CO double bond adjacent to the aromatic ring, which is a meta-director. So if we treated this with Br2 and iron tribromide, we would get meta. So side chains can be oxidized to make carboxylic acids, and again, this is altering the nature of the side chain, in this case turning it from an ortho-para director to a meta-director. And one last reaction, which is kind of odd, and I'm going to go through the mechanism of this, is the Birch reduction. If I treat benzene with metallic lithium in liquid ammonia, I would get cyclohexadiene, actually 1,4-cyclohexadiene. Now those conditions should sound familiar. Those should sound like, well, when have we used lithium in liquid ammonia? We only used it one time, and that was when we took an alkyne and we reduced it to a transalkene. And this is similar, in fact, the exact same mechanism. If you recall that from that mechanism, lithium was a source of 1 electron. And so if I've got benzene and I add 1 electron to it, I'm going to make a radical anion. You could go back and look back at the alkyne chemistry discussion and see a similar process. If that gets protonated, we get this radical species, and if this radical species is in the presence of a good single electron donor, like lithium, we can make the carbanion, which if it gets protonated, gives us this 1,4-cyclohexadiene. If I've got a substituted aromatic ring, it turns out I actually get, depending on the substituent, 2 different isomers of, or 2 different regioselectivities, as it were. And it really has to do with this first intermediate. When I add an electron to make a radical anion, is it better to put that negative charge adjacent to that substituent or not adjacent to that substituent? And an aldehyde, CHO is an aldehyde, is an electron withdrawing group, and it's good to put a negatively charged thing right next to that. So then if I protonate there, the rest is history. The next one goes opposite, and so we end up with this sense of selectivity. On the other hand, if I've got an electron donating group like a methoxy, it's better to put the negative charge on the next position over because of the every other one nature of the every other one nature of resonance with these pi systems and 6-membered rings. It's better to go here or here, not here, here, or even here, it turns out. In which case we protonate here and our next proton ends up over here. So I don't want to belabor this, but I just wanted to kind of walk through that mechanism because it is kind of a reinforcement of the same type of mechanism we saw with alkyne reduction. I'm not really going to worry too much about these because these are single electron transfer mechanisms and they're fairly relatively obscure as it goes. So that's aromatic rings. We talked over the course of our discussion about what is an aromatic ring and what does that mean. How can you recognize that a molecule is an aromatic ring? The main reaction of aromatic rings, and the most important one, is the electrophilic aromatic substitution. You should certainly understand, sort of predict the products of electrophilic aromatic substitution, understand how that happens, and also understand how you get selectivity, excuse me, can't talk today, if you don't have benzene but some substituted benzene. Also, we saw some other reactions at the sides next door to benzene, the benzylic position, and this last but not least, the Birch reduction. All right, we're going to change gears completely. In our next set of discussions, we're kind of done. We've gone through a lot of chemistry related to carbon-carbon pi bonds, alkenes, alkynes, conjugated pi systems, and cyclically conjugated pi systems. Next, we're going to go on and look at functional groups that contain heteroatoms, mostly oxygen, though we will see some nitrogen as well, and maybe a little bit of sulfur. But mostly we're going to look at oxygen. We've seen a lot of functional groups that have oxygen in them, like alcohols, ethers, ketones, aldehydes, carboxylic acids, various derivatives of the carboxylic acids, and that's kind of where we're going from here. All right, thanks for listening, and we'll see you in our next presentation. I won't actually see you because I'm talking to a computer. Anyway, thank you. Bye.